Welcome to this model. Today we are going to see about the transport layer protocols. The original TCP/IP protocol suite specifies two protocols for the transport layer, one is UDP and the other is TCP. Now we'll first focus on UDP, the simplest of the two, before discussing TCP. And then a new transport layer protocol SCTP has also been designed. Now let us see one by one. So totally we have three transport layer protocols called UDP, TCP and SCTP. UDP is an unreliable connectionless transport layer protocol used for its simplicity and efficiency in applications where error control can be provided by application layer process. Whereas TCP is a reliable connection-oriented protocol that can be used in any application where reliability is important. SCTP is a new transport layer protocol that combines the features of UDP and TCP. Now let's see the UDP first, user datagram protocol. It is called as a connectionless unreliable transport protocol. It doesn't add anything to the services of IP except to provide process-to-process communication instead of host-to-host communication. Also, it performs very limited error checking. If UDP is so powerless, why should a process want to use it? So with the disadvantages come some advantages. UDP is a very simple protocol using a minimum of overhead. So if a process wants to send a small message or doesn't care much about reliability, it can use UDP. Sending a small message by using UDP takes much less interaction between the sender and receiver than using TCP and SCTP. Now let's see the table which shows the user datagram having fixed size header of 8 bytes. So this is the format of user diagram. And there are some well-known port numbers used by UDP. Some port numbers can be used both by UDP and TCP. And port number 7 is echo protocol, which echoes received datagram back to the sender. And port number 9 is discard. It discards any datagram that is received. And 11 is users, and it indicates the active users. In Unix, the well-known port numbers are stored in a file called services. Each line in this file gives the name of the server and the well-known port number. So we can use the grep utility to extract the line corresponding to the desired location. And there are some list of well-known ports used with the UDP. Let's see the list. So 13 is the daytime. It returns the date and time. So 17 is the quote, returns a quote of the day. And 19 is the chargen, which returns a string of characters. And 53 is the name server, which indicates the domain name service, and so on. So there are list of port number and the descriptions are given in the table, right? So now let's come back to the header. UDP packets called user datagrams have a fixed size header of 8 bytes. And the fields which are shown in this diagram are, first is source port number. This is a port number used by the process running on the source host. It is 16 bits long, which means that the port can range from 0 to 65,535. If the source host is the client, the port number in most cases is an ephemeral port number requested by the process and chosen by the UDP software running on the source host. If the source host is the server, then the port number in most cases is well-known port number. The destination port number is used by the process running on a destination host. It is also 16 bits long. If the destination host is the server, the port number in most cases is a well-known port number. That is, server means a client sending a request. If the destination host is the client, which means a server sending a response, the port number in most cases is an ephemeral port number. So in this case, the server copies the ephemeral port number it has received in the request packet. And the length is a 16-bit field that defines the total length of the user datagram header plus data. The 16 bits can define the total length of 0 to 65,535 bytes. However, the total length needs to be much less because a UDP user data datagram is stored in an IP datagram with a total length of 65,535 bytes. The data length in the UDP user datagram is actually not necessary. A user datagram is encapsulated in an IP datagram. There is a field in the IP datagram that defines the total length. There is another field in the IP datagram that defines the length of the header. So, if we subtract the value of the second field from the first, we can deduce the length of the UDP datagram that is encapsulated in an IP datagram. However, the designers of the UDP protocol felt that it was more efficient for the destination UDP to calculate the length of the data from the information provided in the UDP user datagram rather than ask the IP software to supply this information. So we should remember that when the IP software delivers the UDP user datagram to the UDP layer, it has already dropped by the IP header. The field is used, checksum field is used to detect errors over the entire user datagram, and we have to check the concept of the checksum because of and the way it is calculated, and to calculate the checksum for the IP and ICMP packet, we will now show how this is done in UDP. The UDP checksum calculation is different from one for IP and ICMP. Now let's see. This is the checksum calculation, pseudo header for checksum calculation. And here the checksum includes three sections: pseudo header, UDP header, and the data coming from the application layer. The pseudo header is the part of the header of the IP packet in which the user datagram is to be encapsulated with some fields filled with zeros. If the checksum doesn't include the pseudo header, the user datagram may arrive safe and sound. So, however, if the IP header is corrupted, it may be delivered to the wrong host. The protocol field is added to ensure that the packet belongs to UDP and not to other transport layer protocols. And we'll see that if a process can use either UDP or TCP, the destination port number can be the same. The value of the protocol field for UDP is 17, and if this value is changed during transmission, the checksum calculation at the receiver will detect it and UDP drops the packet. It is not delivered to the wrong protocol. So you can now note the similarities between the pseudo header fields and the last 12 bytes of the IP header. The calculation of a checksum and its inclusion user datagram are optional. If the checksum is not calculated, the field is filled with ones. And you can notice that a calculated checksum can never be all ones because this implies that the sum is all zeros, which is impossible because it requires the value of the fields to be zeros. So UDP uses the concepts to transport layer, common to transport layer, and first one is it provides a connectionless service, which means that each user datagram sent by UDP is an independent datagram, and there is no relationship between the different user datagrams even if they are coming from the same source process and going to the same destination data packet. That is, it cannot send a stream of data to UDP and accept UDP to chop them into different related user datagrams. So instead, each request must be small enough to fit into one user datagram. Only those processes sending short messages should use UDP. UDP is very simple, unreliable transport protocol, and there is no flow control and hence no window mechanism. The receiver may overflow with incoming messages, and there is no error control mechanism in UDP except for the checksum. This means that the sender doesn't know if a message has been lost or duplicated. When the receiver detects an error through the checksum, the user datagram is silently discarded. The lack of flow control and error control means that the process using UDP should provide these mechanisms. To send a message from one process to another, the UDP protocol encapsulates and decapsulates messages in an IP datagram. And now, at the client side, when a process starts, it requires the port number from the operating system. So, some implementations create both incoming and outgoing queue associated with each process. Other implementations create only an incoming queue associated with each process. You can now notice that here you can now notice that even if a process wants to communicate with a multiple process, it obtains only one port number and eventually one outgoing and one incoming queue. The queues are opened by the client or in most cases identified by the ephemeral port numbers. The queues functions as long as the process is running. When the process terminates, the queues are destroyed. The client process can send messages to the outgoing queue by using the source port number specified in the request. UDP removes the message one by one and after adding UDP header, delivers them to IP. An outgoing queue can overflow, and if this happens, the operating system can ask the client process to wait before sending any more messages. When a message arrives for a client, UDP checks to see if an incoming queue has been created for the port number specified in the destination port number field of the user datagram. If there is such queue, UDP sends the receiver user datagram to the end of the queue, and if there is no such queue, UDP discards the user datagram and asks the ICMP protocol to send a port unreachable message to the server. All the incoming messages for one particular client program, whether coming from the same or a different server, are sent to the same queue. An incoming queue can overflow, and if this happens, UDP drops the user datagram and asks for a port unreachable message to be sent to the server. So at the server side, what happens is the mechanism of creating queues is different. In its simplest form, a server asks for incoming and outgoing queues using its well-known port when it starts running. The queues remain open as long as the server is running. When a message arrives for a server, the UDP checks to see if an incoming queue has been created for a port number specified in the destination port field of the user datagram. So if there is such a queue, UDP sends the received user datagram to the end of the queue, and if there is no such queue, UDP discards the user datagram and asks the ICMP protocol to send a port number unreachable to the client. All the incoming messages for one particular server, whether coming from the same or different client, are sent to the same queue. An incoming queue can overflow, and if this happens, UDP drops the user datagram and asks for a port unreachable message to be sent to the client. When a server wants to respond to a client, it sends messages to the outgoing queue using the source port number specified in the request. UDP removes the messages one by one and at the end, after adding the UDP header, delivers them to IP. So an outgoing queue can overflow. If this happens, then the operating system asks the server to wait until sending any more messages. Thank you.